All right, today our lecture is going to focus on solute transport. And so it's going to build a little bit on the foundations of everything we've learned about flow and allow us to stretch from that to thinking about how things are actually moved around with water itself. So this is just going to be kind of a general overview. And part of what I want you to really understand from this is how might we generate the equation for solute transport, and how might we depict the processes that are taking place, right? So let's get started. So when we think about groundwater flow, there are a couple of components that we're thinking about. We're thinking about what the head is. So what is the hydraulic head as we move in the X, Y, and Z directions, right? And then how does this change with time? Right, so we have maybe flux of water that's coming in, right? We can think about what that means for the head distributions across the system. We also think and know that this groundwater flow, even throughout time, right, is based on continuity principles. So we've talked a lot about this idea of conservation of mass. What comes in should be equal to what's going out of the system itself. We know that we can relate our head levels to this flux of water through the Darcy's law. And so Darcy's flux here, right, which is our, here is our volumetric flux, is another way of saying it. It's our typical more way of saying it, is equal to the hydraulic conductivity multiplied by the gradients of H. And we put gradients of H here like this because that gradient could be in the X, could be in the Y, could be in the Z direction, allows us to talk about it a little bit more simply. And when we put all these components together in a steady state system, we can say that under steady state conditions, right, this is equal to 0. So as we move under steady state conditions, if we solve in all directions, that can be the case. So another way of us writing this is if we have an anisotropic system that's heterogeneous, right? We've talked about this. So we can talk about how things change in the X direction, how the hydraulic conductivity may be preferential in the X direction or less so, and the change in heads in that X direction. The same with the Y and the same with the Z, and under a steady state condition, we can say that's equal to 0. And under transient systems, right, we can say that the that we have here our specific storage multiplied by our change in our head over the change in time. So these are kind of the basic principles that we've gone through when it comes to our class. But let's think about how that might influence the way that solutes might be transported in the subsurface. So let's first take into consideration a term that's called advection. Advection is the solutes transported by the bulk of flowing groundwater, okay? And so let's depict what that's going to look like. So here's injected some kind of contaminant or solute in our system. X is the direction, C is the concentration. Our flow is happening from our left side to our right side. And if we begin to visualize what that is, take a minute, hit pause if you need to. Where would this be sometime in the future? So if we were at some time in the future, this single injection on the system through advection would move through like a slug, right? We see that we have the same concentration. It's just moved with time with our flow in the system. If we had a continuous injection though, right? Here we've said single injection versus continuous, we would actually have a concentration over space that's been maintained at the same concentration, but covering the distance for which that can flow over the time it's allowed to. So again, when we start to begin to conceptualize these, think to yourself and start to draw these out as you're taking notes. So We can think of this as the average linear velocity. And we've talked a lot about that average linear velocity, right? That average linear velocity is just our gradient, right? It might look different, but it's the change in head over the change in length multiplied by our hydraulic conductivity divided by our effective porosity. And if we do this in the x direction, that's exactly what we're showing. Now, what this means though, right, when we think about this idea of the contaminant moving at an average linear velocity is there's non-reactive, right? Or they are conservative solutes. So an example of a conservative solute oftentimes is something like chloride or bromide. These are oftentimes things that are not interacting with the subsurface in these systems. And so you can think of those as something that's moving through and having this kind of linear velocity within the system. We can then say, okay, if we understand what our average linear velocity is, and we also understand this idea of our mass flux. Our flux is just going to be equal to our velocity multiplied by our NE, right? So we get back to the Q, the QX times our concentration. That's going to be the flux of our system here. And then we can come up with actually what is advective transport. So our advective transport says the change in our concentration over the change in time here is equal to the negative linear velocity multiplied by the change in concentration over the change in space. Now, I'm going to ask you to be able to remember to some degree or to identify, let's say, what these equations look like, but you're not going to be applying this equation necessarily in our class. So here's another one I want you to think about. So this is slightly different. I want you to think about drawing the concentration at time 1, 2, and 3 due to transport by advection. So let's go ahead and think about that. How would you draw the transport by advection in the system at 3 different times? So at time, we would have our first initial input. Our second time, we would see it move to the next place, and our third time, and so on and so forth. But one of the things that we have to think a lot about is that the advection of a solute, right, T at 0 to T at some time, this is the advective transport of a solute. But the actual transport of a solute does not look like the advective one, right? It's not just the linear velocity. We have all of these movements that are taking place throughout time. And what does that actually end up looking like, right? So this would be what our advective transport looks like at the top. If this could just automatically move to here based on the velocity of the system. But instead, what we actually get is that this moves, and because it has to take all sorts of different types of pathways, it begins to spread. So we can think of advection as the slug of a chemical moving through the system itself. But we actually really need to begin to think of advection and other processes that are governing flow as well. So one of these processes is this idea of diffusion. So we can begin to think of diffusion, and let's take a look here. As this bubble passes through of a contaminant in time, what are we beginning to notice about the bubble? Make some notes. What are you seeing? What's taking place? Why don't we watch that just once more again? We have high concentration, it's coming out, it goes over location A. We see this high concentration come up as that bubble moves over A. We can see that bubble of a contaminant moving along again. And now we see a raise in well B, or maybe C, but it's not nearly to the same degree of the system. And then finally, when we get towards the end, you can almost maybe barely detect what's happening because the concentration isn't that strong. So diffusion. Diffusion is ion molecules moving from areas of high concentration to areas of low concentration. We can think of this as migrating randomly, bumping, or no memory. It is a function of temperature and weight, and it dominates in aquifers that are confining. So if we think of Fick's first law of diffusion itself, we know that our flux, right, the mass flux of the solute is equal to our diffusion times our concentration gradient. So we have a mass divided by some unit length squared over time. So we can say our diffusion, negative diffusion coefficient over here, we have our concentration, and then we have our change in the X. And then we have Fick's second law of diffusion equation, which says the change in concentration over time is equal to negative D times the partial derivative of our concentration in the X space over time. So we think of this and we can say, okay, if we draw our concentration this time at time equals 1, 2, and 3 due to transport by diffusion and diffusion only right now. So we're not saying that there's any ability to move through advection just through diffusion. What we would see is we'd say, okay, we have our time at 0, we install this plug, and then as our time continues in distance, we see diffusion taking place and the solute moving away from the system here. Then we can think of thinking about drawing our concentration at time 1, 2 due to transport by diffusion. And in this instance, we have our distance here, we have our concentration, and we can say, okay, at T1, T2, T3 in the X direction, this is going to be the concentration of our solutes as we move through there, okay? So then we can also think of one other thing that's called dispersion. So diffusion, now dispersion. This is the third thing that's going to be impacting the behavior of our system. And this is spreading and mixing of constituents due to variations in velocities themselves. So the first one was due to variations in concentrations or due to moving from a high concentration to a low concentration. And this has to do with variations in velocities, right? We know that water does not travel at the average linear velocity. It travels at many different rates moving through there. Now, depending on your system, right, depending on how many different rates you have, is going to control the spreading of your system. So we can say here, you can have advective transport, right? Because it's being moved, right? Something has to be mixing it in and of itself. And then how that actual mixture is taking place is the dispersion that goes along with it. So here we have our advective transport, which is going to be our average linear velocity multiplied by our effective porosity times that concentration, right? That's what we have here. And then we have our dispersive transport, which is our again, our effective porosity, our dispersivity now, and the change in the concentration over some change that we're having in our I direction, in our velocity direction. So, or in the velocity term that we have. So we have advection minus dispersion. And so our flux here is going to be equal to our advective component versus our dispersive component. So go ahead and take a minute and just think about the factors that are going to be governing flow in our systems, right? And go ahead and draw on some flow vectors, and then describe how those velocities might vary, right? How might they change? And what is the dominant, what is dominant in the dilution of a solute? So we can say, okay, if we think about here, right, in this system at the top, this might be two different flow vectors. And so we see that different pore sizes are going to govern our what's happening. And then within any given pore, right, so different pore sizes, we're going to have different flow vectors. And then within a pore, we're going to have different velocities in a pore, right? Where we always have drag on the sides and the highest velocity in here. And then we're going to have different ways or different pathways around each grain. So we have this effect taking place, we have this effect taking place, and then we have this effect also occurring in the system itself. So let's say at time 1, what is advection and dispersion going to look like, right? So let's say here we have a given condition, right? We have flow taking place, we have this injection, and it started as a solid slug, right? But what we begin to see is that that solid slug spreads out, right? Where we have parts that are moving faster in the system and parts that are moving slower in the system. And so it begins to create, and at least in this instance, something that looks much more like a bell-shaped curve. So we can have these processes that are taking place. But what happens if this constituent also is able to be used? What if it's able to be used by microbes? Or what if it's used in another reaction? So then we can also have decay. So a certain concentration starting at the initial condition and at some time 1, right, we can have still that spreading. So some of it being able to move faster, some of it being able to move slower, right? But then we can also have an overall reduction in the system because this chemical constituent is being consumed by a thing. What happens if, though, we have something that's called advection and we have dispersion, but then we have absorption taking place? Again, we start at this initial condition in our system. And with absorption, what we can see is that we're having a slug that's moving through. It looks very much like what happens with advection and dispersion, but at T1, it hasn't made it nearly as far. And the reason for that not making it as far is you can think of all of these grains, right, that our surface area that's in the subsurface, and certain proportions of these grains are being picked up, or sorry, a certain proportion of the chemical is being picked up, and then it's finally being actually knocked back off. And so you again get this kind of slowing of the effect that would normally take place if you have an advection and a dispersion. So if we think about the different processes that are taking place, we have groundwater flow moving in the left-hand direction, left to right on this page. If we only imagine it as advection from a constant source, we might imagine it like this in the blue dotted line. If we add in the idea that water is going to move from areas of chemically high concentrations to low concentrations, that's going to be our diffusion, and that it's going to take different pathways, not the average linear pathway, but it's going to move according to pore geometry, which is going to be our dispersion, we'll end up with something that looks more like this. If we add absorption to that process, right, it's going in the same amount of time, we're not going to see the same proportion of spreading that happens in that system. And then if we add degradation to that environment, we're going to actually even remove it and reduce it to a greater degree. So when we think about the idea of the transport of solutes in that flux in the X, the flux in the Y, and the flux in the Z direction of materials, right? So that's a mass that the mass changes must be equal to the differences in mass changes entering and leaving the system. We can create an equation that looks like this. And then if we substitute that with a sum of the advection and the dispersion, we can cancel out our effective porosity on both sides. And we end up with an equation similar to what we have seen before, but in this instance, we have our kind of dispersion processes that are happening at the top. And these are actually incorporating both dispersion and diffusion, dispersion and diffusion on the top. And then we can see about what's taking place on the bottom, which is our advection. And we think about these in the X, the Y, and the Z direction, just like we think about our changes in our concentrations in the X, Y, and Z directions as a result of just advection itself. And so these two components themselves come up with the concentration, the change in concentration, and over the change in time in our system.